Hello students, this is Professor Chalai, and in this video we're going to start chapter 8 as we look at more advanced theories of covalent bonding. And for this video we're going to begin with our first topic in this chapter, valence bond theory. As always, you can follow along with our chapter 8 workbook. By the end of this video, you should be able to describe covalent bonds in terms of these atomic orbital overlap, and also give examples of sigma and pi bonds. Let's get started. So we looked at, before we looked at atomic orbitals, right? Where, for example, we had s orbitals that sort of are shaped like spheres that surround a nucleus. So if I use green as a nucleus, that would be our nucleus. So this would be an s orbital. And then we also talked about p orbitals that sort of looked like little dumbbells. I'll use red for one lobe and blue for the other. And again, green, the nucleus would be in the middle here. The two different colors are often used to represent p orbitals because they have, like a wave, they would have different signs, right? One region would be positive and one would be negative. It doesn't matter which color is which. Maybe the red part is the positive part of the wave and the blue part is the negative part of the wave. And we know that there are three different p orbitals. There's this one along the x-axis, which we'll call px. There is the one along the y-axis, which we'll call py, and so the blue might be here. And then there's the pz axis that goes in and out of the page that will be difficult to draw. So these are atomic orbitals, and we talked about how when atoms come together to form molecules and form bonds, covalent bonds, they share the electrons. So they're shared electrons that are in these orbitals. So let's look at an example of atoms come together to form the molecule of water, H2O, right? The electron configuration of hydrogen is just one electron in the 1s orbital. An electron configuration of oxygen is, I'm just drawing all of the orbital boxes. So we have 2 in the 1s, 2 in the 2s, and then we have 1, 2, 3, 4, 5, 6, 7, 8 electrons total. Usually we're only focused on the valence electrons, so we can replace the 1s with, for example, just the helium configuration. Okay, in the valence bond theory, what we're dealing with is basically the overlap of orbitals, atomic orbitals of hydrogen and oxygen that are half filled. Remember, electrons always want to be paired up as much as possible. So when they form bonds, they're going to be interacting with their half-filled orbital. So this electron would pair up with maybe that electron over there. And then if you have a second hydrogen with another one electron sitting by itself, that one electron would start to pair up with this other electron over here. And this is the picture of what's happening as these form bonds. And so you have oxygen, and let's see if we can erase that to have a little bit more clean picture. So this new bond, this pair that's formed here might be this new bond with hydrogen, and then this other pair that's formed here might be this other new bond with hydrogen. In this first pair, right, we have one electron that's from oxygen, one from hydrogen. In the second pair, the same thing. And that's what we, at least from a Lewis structure, that's how we understand bonding. And then these other two pairs, just let me point them out. This pair and this pair in the valence orbitals, they're not involved in the bonding. And so that's why we draw them as lone pairs, just staying on the oxygen like that. Okay, so that's essentially what valence bond theory is all about. Valence bond theory is simply the description of a covalent bond in terms of overlap of half-filled atomic orbitals. Atomic has one T. Okay, so instead of just thinking about the electron configuration here, let's think of what this physically looks like. So we have oxygen, right? And what's interacting here are the two p electrons. So we know the p electrons have orbitals that I'm going to just try it as a lobe. Here's one lobe, here's the other lobe, and on this end it's interacting with a hydrogen. So here's our hydrogen, and I'll draw it a little bit closer. Hydrogen, and hydrogen, the 1s electron that it's interacting with, right? So I'm drawing this 2p orbital and this 1s orbital. We know that the 1s orbital is just a sphere-like orbital. So when where it's interacting in this region in between, let's use a different color. This is the region in between where it's interacting, where it's overlapping. That's the bond. Now, what does that look like? Let me show you a clear picture. So we're looking at a situation like this, where we have an s orbital from the hydrogen, a p orbital from the oxygen overlapping, and the region where they overlap sort of looks like a sphere as well, doesn't it? Maybe if you squint your eyes, sort of looks like a sphere. So because of the overlap region kind of looks like a sphere, it kind of looks like an s orbital. Kind of looks like an s orbital. But we can't call it an s orbital. S orbitals are atomic orbitals, and this is sort of a bonding in the region between the hydrogen and the oxygen, right? There's an orbital in between there, if you will. That's what that resembles. So it's like an s orbital, but it's between two atoms. We need to call it something. Why not use the Greek symbol for s instead of just calling it s? And that's where sigma comes in. This is sigma. Sigma. And so we'll call that a sigma orbital or a sigma bond. Why bond? Because it's actually between the two atoms. In fact, there are three different cases where you can get sigma orbitals when the orbitals of two different atoms overlap. If you have an overlap between an s and an s orbital, you'll get a sigma orbital in between. If you have an overlap between an s and a p orbital, you'll also get a sigma overlap orbital in between. And if you have two p orbitals that are sort of aligned with each other, where they overlap would also look like an s orbital. So those are the three situations: two s orbitals, an s and a p orbital, or two p orbitals. If they overlap, they would form a sigma bond. A pi bond are formed when you have the overlap of two p orbitals, right? So let's draw this here. P orbital, another p orbital. I need to draw them bigger. P orbital from one atom, and then you put another atom right next to it, and you have another p orbital from that, like this. You can see that the overlap region, the red I'm shading and now the blue I'm shading, what is this resembling? Another p orbital, right? I'm making it even bigger. It's looking exactly like a p orbital. So we're not going to call it p though, we're going to use the Greek letter for p, which is pi. We're going to call it a pi orbital, or a rather, in fact, in this case, a pi bond, because it's between the two atoms, right? So pi bonds are formed when you overlap two p orbitals. And there's there's going to be two situations where that can happen. They're aligned along this axis, or they're sort of aligned in and out of the page, which is also difficult to draw. So sigma bonds are formed when s or an s and a p or two p orbitals overlap. Pi bonds are formed when two p orbitals overlap. But here's the important thing to note. Whenever two p orbitals overlap, they will first try to form a sigma bond, and then they'll try to form a pi bond. Why? Because they just try to align each other like this to form a sigma bond first. That's just what they do. So in this way, we can sort of figure out when two atoms come together to form bonds, whether they're going to be forming sigma bonds or pi bonds. And so let's look at these examples. Two hydrogen, they only have one s electrons, right? So we know that when they come together, they'll form sigma bonds, or one sigma bond. What about oxygen and oxygen? Okay, let's look at that. So oxygen, we just did the electron configuration of oxygen. This is 2s, this is the 2p, right? And so we'll have this situation. Not what I wanted to draw or erase. There we go. All right. If you bring another oxygen, right, right next to it. Let's use, I don't know, red for this electrons. You can already see which set of orbitals are going to overlap. This one with this one, and this one with this one. So basically what we'll have is overlap of 2p electrons. Overlap of 2p electrons. There's again two different sets of overlaps, so there's going to be two different sets of bonds, right? And that's why we have a double bond. And because their overlap of 2p electrons, the first time they overlap, they're going to form a sigma bond, and then the second time they overlap, they're going to form a pi bond. So it's going to be one sigma bond and one pi bond that's formed. So we see two bonds. The first one is going to always be a sigma bond. The second one is going to be a pi bond. And this is true always. Nitrogen, same situation, right? Nitrogen, the electron configuration are going to be helium, 2s, and then 2p, kind of like this. So it could form three bonds by pairing up with three other electrons from the neighboring nitrogen. It's the overlap of the 2p atomic orbitals. The first time they overlap, it's going to form a sigma bond, one sigma bond. And then the second and the third time they overlap, they're going to form pi bonds, so two pi bonds. And that's where the three bonds come from. In general, if you see a single bond, so single bond, it's going to be sigma. If you see a double bond, the first one is going to be sigma, the second one is going to be pi. I draw arrow to one or the other, but it doesn't matter which one's which in this example. If you see a triple bond, one of them is going to be sigma, and then the other two are going to be pi. That's the rule. So let's look at this structure. We don't even have to think about what atomic orbitals are being bonded here. We can just count the bonds that we see. So the first bonds everywhere are going to be sigma. So that's 1, 2, 3, 4, 5, 6. And then the first bond there, 7 sigma bonds. And then the second bond there is going to be 1 pi bond. So those are sigma and pi bonds in those molecules. Let's try it again, this time drawing the Lewis structure. If you haven't done so, please pause the video here, do all of these, and then unpause, and then we'll go over them together. Okay, let's draw the Lewis structure for carbon. Methane, sorry. We have carbon, we know hydrogens are terminal, so we put them at the ends, kind of like this. How many valence electrons do we have? Well, we have 4 from the carbon, and we have 1 from each of the hydrogens, so it's 4 times 1, we get 8. But we already have 8 electrons in the bonds, so we have 0 left over, so we don't have any lone pairs anywhere. Okay, how many sigma bonds? 1, 2, 3, 4 sigma bonds, and 0 pi bonds, because there's no double or triple bonds here. As soon as you don't see any double or triple bonds, you know you don't have any pi bonds. We did the case of water before. It kind of looks like this. Lone pairs over there. We have 1, 2 sigma bonds, no pi bonds. If you haven't done this one, please do so now. But this is carbon attached to 2 hydrogen, attached to a nitrogen, attached to a hydrogen. In case you're wondering, this is the skeletal structure where you start with for your Lewis structure, and then you need to fill in the valence electrons and the double bonds if necessary. How many valence electrons are we working with? We have 1 for each of the hydrogen, and there's 3 hydrogens. We have 4 from the carbon, and we have 5 from the nitrogen. So 3 by 1 is 3, plus 4 is 7, plus 5 is 12. We already have 1, 2, 3, 4 bonds, so we need to minus 8. 12 minus 8, we have 4 valence electrons left. I usually give them to the most electronegative element, which in this case is nitrogen. Okay. Let's look at our octets. All the hydrogens are fine, they're terminal, we don't need more electrons on them. This carbon though has 6 electrons, 1, 2, 3 bonds, 6 electrons, so let's share these two, like that. Nitrogen looks happy, it has 3 bonds and 2 from the lone pair, so it's happy. So, how many sigma and pi bonds? Well, all the single bonds are a sigma, 1, 2, 3, and the first bond here is also a sigma. And then, so we have 4 sigma, or bonds. And then the second bond here in the double bond, that's 1 pi orbital, 1 pi bond. So this is no longer a skeletal structure, this is the Lewis structure. All right, so that will bring us to the end of valence bond theory. Just know that it's the overlap between atomic orbitals, and while we're only looking at the overlap between s and p orbitals, there are 2 different possibilities. A sigma, when it's either an s and an s, or s and a p, or 2 p's, the very first 2 p's. And then if there are other 2 p's that overlap, they'll form pi bonds. Or, in short, single bonds are sigma bonds. Double bonds and triple bonds, the first one is going to be a sigma bond. The second one, or the second and third ones, are going to be pi bonds. All right, in our next video, we're going to look a little bit more in detail about, we're going to look at hybrid atomic orbitals. I'll see you then. Bye.